Okay, so in this video, we're going to be looking at some of the theory of gases, looking at the kinetic theory of gases, and we're going to use it to explain what happens when we use a U-shaped tube. So let's first look at what I mean by a U-shaped tube. Okay, so this is our U-shaped tube. You can see that the reason it's called that. So we've got on the left-hand side at the top, it is open to the air. On the right-hand side, it is sealed and connected to a syringe, which is going to enable us to vary the volume of the gas that is above the water in the U-shaped tube. And by varying the volume, it's going to allow us to vary the pressure. And we're going to look in this video how the system responds to changes in pressure. So just to state from the start, we're going to assume that temperature is constant throughout. So we're going to apply Boyle's law, which states that at constant temperature, the pressure of a gas is inversely proportional to its volume. So that's what we're going to be looking at for this video. So let's get started. So that's just labeling where those different sections are so you can see them a little bit better. So let's see how the system responds when we vary the height of the plunger or vary the volume. Okay, so I'm going to set this going. So what I'm going to do is we're going to push down the plunger and decrease the volume in there. Now we can see that the system responds by the water level rising on the left-hand side, but what you might not have spotted is that the water level dropped on this right-hand side there. So on the left it goes up, and on the right it goes down. And the height change is identical. And then what I've done is I've just reversed that change. So I've then increased the volume of gas on the right-hand side, and then the system has reversed that process. So the question is, why does that height change? What is causing the height of the water to change on both sides? So what we're doing in actual fact is we are applying a force to the plunger. So we're doing some work, and that's changing the volume of the gas on the right-hand side. And more specifically, it is decreasing the volume of gas on the right-hand side. So what that means is any gas particles are going to be colliding with inside the sealed system there. So if we've got a smaller volume, we're going to get more collisions per second, and that's going to manifest itself in a greater pressure on the water. So as the water molecules collide with the air particles, there are more collisions per second. That's going to result in a larger pressure and a larger force on the water from the gas. So the pressure on the other side of the water remains the same because it's still at atmospheric pressure. So if we look at it in terms of force, force is pressure times area. So if there's a larger pressure on the right-hand side for the same area, that's going to result in a larger force. So there's going to be a force pushing water around from the closed side to the open side. And the reason it does that is that then allows the volume of gas to increase again, which decreases the pressure, and once the pressures become equal to each other, we reach an equilibrium position there. And if we look at the reverse process, so what happened in the second half of the video is we pulled out the plunger. So what that does is it increases the volume of the gas. So you get fewer collisions between the gas and the water, so the pressure on the water decreases. So then the opposite process happens now, so the pressure is greater on the open side than on the closed side, and there's a resultant force to move the water around until the volume decreases and we get to a new equilibrium position. Okay, so far we've just seen when the area is consistent throughout the U-shaped tube. So we've just essentially seen pressure difference and force difference essentially end up being the same because the area is the same. So what would happen if we had a U-shaped tube where the cross-sectional area is different on each side? So say, for example, the closed side has double the cross-sectional area of the open side. How does that change the experiment? So when the area was the same, the height change on both sides is identical. So if The closed side goes down 5 centimeters, the open side goes up 5 centimeters. So the question is, how is it going to change when we factor in the fact the area is different? Well, so if we're going to get the same force, what we need to do is have half the pressure on the side that has double the area, because then the force on both sides are going to be equal to each other. So that's how it's going to be different. So in both scenarios where the areas are the same or the area is different, the force on both sides has to be equal for it to be in an equilibrium position. But in this scenario, the pressures do not have to be equal to each other. It's the forces that have to be equal to each other there. Okay, so let's think about this another way. So say we think about it just in terms of the volume of the water. So when we push down the plunger, what we're essentially doing is we're moving a fixed volume of water from one side to the other. So if we have doubled the area, to have the same volume, that means we're going to have half the height, essentially. So you can see that represented at the bottom there. If we can see that to have the same volume, if you have double the area, the height of the water is going to be half. I'm modeling them as cylinders, but it wouldn't really matter what shape we used, it'll be the same as long as it was regular. So that's another way of thinking about how this works and how the height change would be different. So what we'd expect to see is the height change on the left-hand side should be double that on the right-hand side if the right-hand side has double the cross-sectional area. Okay, so that concludes this video looking at the U-shaped tube. It was just a quick look at an application of Boyle's law, but I hope you found that interesting and useful to help see how we will use these concepts to explain different phenomena.